Hello everyone, my name is Mauricio Verano. I am a PhD student at Eindhoven University of Technology, and today I'm going to talk about how to describe and generate a block-based environment from a context-free grammar. This is joint work with Tijs van der Storm. Okay, so first we need to know what a block-based environment is. So a block-based environment is a visual programming environment that uses jigsaw-like blocks to represent language constructs. The most popular block-based environment is Scratch, which is a block-based environment for children to create animations based on code. A block-based environment is divided in three main parts: a toolbox, canvas, and an execution pane. The toolbox itself is divided into categories, and each of these categories may contain one or more blocks. Then, users take these blocks to build their programs. And the way they create their programs is by dragging and dropping blocks from the toolbox into the canvas. Finally, users can execute their programs and see the results on the execution pane. In this talk, I will be focused only on the syntax of the languages, but our approach also covers the execution of block-based programs. Okay, so here we have a block representation of an if statement. As we notice, there are several properties in this block. So for instance, it has a color. It also has some holes for inputs. So this one is a value input. So a value input is used for expressions because it allows users to stack blocks in an horizontal way. Then we have labels. So labels are important for end users because they give some hints to the users about what the purpose of the language is. We also have different types of input. So this is an statement input, and it is usually used for stacking blocks in a vertical way. And finally, we have connections. So connections are important for block-based environments because that's the way users can create programs. So either they can put blocks on top of it or below them. Moreover, a block can have two ways of representing the inputs, so either as inline or external. It's important to notice that this does not have any impact on the syntax of the language, but it has an impact on the UI of the language. Likewise, block-based environments have some built-in data types. So these are a few examples of those data types. So they have custom blocks for strings, IDs, booleans, floating point numbers, integers, images, and even for angles. This is interesting from the DSL perspective. We created a tool called Kogi. So Kogi is a tool for describing and generating block-based environments from a context-free grammar. Kogi is currently implemented in Rascal, but our approach should be extensible to other language workbenches. So to develop Kogi, first we reverse engineer block-based environments, and based on this process, we created a generic structure for describing them. Kogi first takes as input a grammar, and then it pre-processes the grammar in two ways. First, Kogi removes all the disambiguation rules because they are not needed for a block-based environment. And second, it inlines all chain rules. So we notice that this has a huge impact in the resulting environments. So with this pre-processed grammar, then we make a transformation from the grammar into this generic block-based structure. And then we create a block-based environment. So the resulting environment is built using Blockly for the rendering of the blocks. Okay, so now let's see it in action. So we are going to create a language for allocating computing resources in Amazon Web Services. In Amazon Web Services, you can allocate your computing resources either by using the web form or using a JSON file. So the first step is to define a grammar for this language. So we define this grammar in which a resource is defined as a list of instances, and each instance has 5 parameters. So an image, a CPU, a memory, and storage, and IPv6. The image, it could be any of Amazon Linux, Red Hat Enterprise, or on some others. The CPU and the memory are modeled using integer values. Then the storage contains a storage type and the size of the storage. And finally, the IPv6, it just represents if the instance supports IPv6 or not. Okay, so now let's move on into Eclipse. So here, this is how Rascal looks like in Eclipse. So we have the same grammar I showed you before, but now I'm going to start the Rascal REPL and I'm going to import a module I defined before. So this module essentially takes the grammar as input and it will generate the block-based environment using Kogi. So when Kogi generates an environment, it produces 2 files, one which represents the block representation and the other file, which is the index, is just a tiny application to render our block-based environment. So let's open it. And this is the resulting block-based environment. So here we can start dragging and dropping blocks from the toolbox into the canvas. And for instance, here we define an instance of our resource and we are creating an instance. And then, well, we can define the values of all these parameters, so the integers and if it does support IPv6 or not. If we lift the mouse over a block, then we get these tiny labels, and those labels are also derived from the grammar. Here we are defining another instance, but now we will show that we can have the inputs as inline inputs. Okay, so now let's have a look how we create this block-based environment. So Kogi makes a mapping between production rules and blocks. In the first row, we see the definition of a resource. So a resource is defined as a list of instances. In the block representation, a list of instances is represented with statement inputs. Second row, we see the definition of an instance, and an instance is defined by 5 non-terminals. Therefore, in the block representation, we have holes for 5 different blocks. And then memory is defined as an integer value. So this is one of the benefits of inlining chain rules, because here we only have one block. If we do not inline chain rules, then we will have one block but with an extra hole, and then users will have to drag and drop an integer block to being able to define the memory. And finally, the storage is defined as the storage type and an integer value. So the storage type is another non-terminal. That's why we have a hole in there. But the integer value, it's replaced there directly thanks to the inlining of chain rules. We applied Kogi to several case studies. So the first one is sonification blocks. Sonification blocks is a block-based language created for teaching students music production. So this language was already implemented as a block-based environment. So what we did was to reverse engineer the block-based environment, and we defined a grammar for it. What you are seeing on the slide is the resulting block-based environment generated by Kogi. Similarly, we wanted to use Kogi with a more programming-like language, so we used Pico. Pico is a tiny programming language that contains some declarations, expressions, statements, and so on. Finally, we have QL. QL is a domain-specific language for defining questionnaires. It was interesting because these questionnaires are often described by end users and not necessarily by computer scientists or programmers. As a further research direction, we identified four. First, with Kogi, we were able to describe and generate a block-based environment. But we noticed that there were some limitations for describing some aspects of a block-based environment. For instance, the layout of the blocks. Second, the block metaphor is really powerful, but we notice that some aspects are easier to describe using just plain text. So that's why we consider an hybrid language between text and blocks an interesting approach. This is similar to what we see with spreadsheets, in which we have the grid, but the way we enter the formulas is in plain text. Third, with Kogi, we are able to execute block-based programs, but we can only see the final result. So we cannot have a look at the intermediate computations or to add some debugging features. So that's an interesting further direction. Finally, we consider error marking an interesting research direction because so far we can only see the errors if we open the console of the block-based environment. It would be interesting to being able to point out where the error is in a block-based environment. To conclude this talk, first I introduced Kogi as a first step to integrate block-based syntax into language workbenches. Then, with Kogi, we want to increase the adoption of the block metaphor for DSLs. So current literature has shown that block-based environments are closer to end users, especially when they don't have a background in computer science or programming at all. And finally, with Kogi, we are able to reuse existing languages. So we can reuse existing language components like type checkers, parsers, interpreters, and so on. With this, I conclude my talk. Thank you so much for your attention.